What's up? In this video I'm covering this novel paper called Multimodal Few-Shot Learning with Frozen Language Models by Maria Tsimpukeli, Jacob Manick, Serkan Kabi, Ali Eslami, Oriol Vinyals, and Felix Hill of DeepMind. So what this paper shows in a nutshell is that they have this model called Frozen, where basically they take a huge pre-trained language model such as GPT-2, they freeze it, hence frozen, and they basically train this vision encoder so that they can parse images as well. So it will just convert images into like tokens which are compatible with the language model, and then they show that they can have this model do few-shot learning across different tasks which involve both the visual cues as well as the linguistic cues. To make it a bit less abstract, let me show you this example to show you what I mean. So this is an example of an input that goes into this frozen model. So we have an image, it will be tokenized, then we have this person is like, and then we have this smiley because this girl is happy, this person is like sad, and finally we prompt the model with this image, and we prompt it with this person is like, and as we can see the model generates this like terrified smiley, a dot, and end of a sentence token. Okay, which is what we've expected, which is really cool. And okay, thing to keep in mind this during this whole video is that these examples are curated. They mentioned that multiple times. So again, the whole point is that they can have this few-shot learning capability rather than they have like a highly performant model on all of these tasks. Okay. Nonetheless, let me show you this one. So this was invented by Zacharias Janssen, Thomas Edison, blah, blah, blah. So the point here is that just looking at this image, you can't deduce what's the answer, whereas here you could have. And so as you can see, the output here is the Wright brothers dot end of sentence token. So the whole point here, as we'll soon see, is that the language model can now pull the factual knowledge in, and we can answer questions like this because of the language model, not because of the vision portion of the model. Okay, let's dig deeper into the paper now. So that was a high level, like a glimpse of this paper. Basically, they can handle both modalities, and they can learn. The more examples you give the model, the better it becomes. That's really cool. Okay, let's now dive deeper. When trained at a sufficient scale, autoregressive language models exhibit the notable ability to learn a new language task after being prompted with just a few examples. And this should be familiar to you. If you haven't watched my video on GPT-3 or the original Transformer paper, do check them out. I'll link them somewhere here. But basically, what those models showed is the following, especially the GPT family of models from OpenAI. They showed that even though the model was trained as a language model, so basically you have an unsupervised task of next token prediction, and that's everything, and they show that it can actually do machine translation, for example. And here's an example of how that looks like. So we have a one-shot setting here where we prompt the model with translate English to French, and then we give it one example, see otter to le trait de mort, I don't speak French, and then you prompt it with cheese, and you have this symbol, and the model will actually learn how to translate this, so to perform machine translation, even though it's never seen such a task during its training. And here we just have additionally a few-shot example setup where we have multiple examples, and then we prompt the model to translate, and they show that with these multiple examples the performance just gets better and better. Obviously it saturates after a certain point, but like the trend is clear. Okay, so that's the first thing. Now here we present a simple yet effective approach for transferring this few-shot learning ability to a multimodal setting, and in particular they focus on vision, as we'll soon see. Okay. Finally, here's a motivation behind all of this. So despite these impressive capabilities, such large-scale language models are blind to modalities other than text, preventing us from communicating visual tasks, questions, or concepts to them. So that's the reason they kind of integrated this vision component. Okay. Let me now explain to you how this whole system looks like and how it works. So the system as a whole is pretty simple. So we have a language model, as you can see here, and it's frozen, so the parameters are all frozen, and we have this vision encoder. So just to be a bit more specific, they were using GPT-2 for the language model, they were using nf-resnet for the vision encoder, but that's not that crucial. You can pick some other language model, you can pick some different vision encoder, maybe something like vision image transformer, but that's not that important, like the fact that these components exist and they are wired the way they are. Okay, so So what they do is, so they first need to kind of adapt the image into the input that the transformer model is expecting, and that's these tokens. So what they do is they have this vision encoder, and it will output after some pooling layer a vector. And what they do is they take a linear layer, they just project this into this novel space. Let me draw it like this, and the dimension will be n times d, where basically they found this n to be like the best value was 2, but that's not important. As you can see here, they have only 2 tokens, but it can be an arbitrary number in general. So d is, that's important. D is a dimension that's the same as these tokens that go into language model. So obviously that's the prerequisite so that we can feed these tokens into the language model that come from the image. And so that's the image part. Now, how do they train this is fairly simple. So basically, I think it would be wiser to write this down as, so we have start of sentence token here. And all of these other words will be kind of translated here. So A will get here, this small will be here, etc. So we'll have small here. And so now what you're trying to do is to predict the target sequence. So as you can see here, so let me just focus on predicting the word small. So the word small will have as a context these image tokens that came here, as well as this start of sentence token, as well as A, because we have causal masking. Obviously, you don't want to have, if you saw small in the input, then you're kind of cheating, and it's easy to predict the output small. You can just kind of copy the values, and the transformer would learn how just to copy paste the values, and that's not what we want. We want to predict tokens. So that's how the task would look like. Basically, here you'd have you'd output a distribution the usual way. So you're just trying to maximize the likelihood. So here maybe we have some distribution, and we find the token that corresponds to the word small, maybe this one, and we'll just want to maximize this to 1 and push all of the other probabilities down to 0. And we do that by just simple like cross entropy. So it will be minus log of p. So when p goes to 1, the loss goes to 0. And so in a nutshell, that's how the system works. That's how it's trained. The gradients are backpropped through these weights, which are frozen, and these weights are then tweaked, so that basically what happens is that this vision encoder learns such representations so that they're useful in order to do this captioning task. Okay, and that's the whole system. It's fairly trivial. Let me now show you how they use this thing. And here we have in the first example, so we have a vision encoder. So we have an image, we encode it into these 2 tokens, and then we prompt it with like this text. So question, what color is the car? And the model generates blue, and then end of sentence token. So by the way, just a short remark here, they actually, even though you can see here a word and a single token, what actually in practice what they do is they use this tokenizer called sentence piece. So this both or this word small may be like separated into subwords, maybe this SMA part will be we'll have 1 token associated with it, and then LL will have second. So that's just an example. But in general, you'll have more tokens than you have words in your sentence. Okay, just a minor detail. And so this is one of the tasks that they're gonna evaluate this model on. The second example here will require the model to have some knowledge base. And additionally, I forgot to mention that the captioning, so during this captioning training, all of the named entities are masked. So if you have a name like Aleksa or something, you'll mask it with a person. So you'll just put a person instead of a name there. So that means that this vision encoder cannot learn those named entities, obviously, because it never saw named entities. And so the examples you see here, like this model generated Steve Jobs, that certainly didn't come from the vision encoder. And that's an important thing I want you to notice here. So the knowledge that Steve Jobs was the guy who invented the iPhone actually came from the language model itself. So that's important. And the third task they evaluate this model on is this fast binding task, where you present the model with the image, then you say, you kind of have this made up word called dex, and you just want the model to associate this visual category of an apple with the novel word dex. And you do the same thing here. You have an orange, Blicket, and finally you prompt it with an image and you say, question, what is this? Answer, and the model generates, this is a DEX. So we saw DEX is apple, so it properly generated, this is a DEX sentence. Okay, so having said that, let me now kind of see, let me show you the quantitative results they got, because that's interesting. Before that, just a short remark here. So they say here, in contrast, our work enables strong generalization to new multimodal tasks, blah, blah, blah. What I want to say here is I don't like this part because basically we don't even have a strong definition of what strong generalization is. And the closest thing I could think of was François Chollet's paper on the measure of intelligence, where he described this terminology where he basically says that all of the current models pretty much that we have in deep learning field and machine learning are only like able to do this local generalization, whereas this broad generalization and extreme generalization is something that only humans can currently basically do. And so yeah, I pretty much agree with him on this one, because this language model that they use in Frozen has seen like a lot of data. So that means it has a lot of experience, which we need to count in when we calculate these generalization capabilities. So arguably, because of all of that like immense amount of experience, you cannot actually claim that it's generalizing like strongly. It does generalize, but like just the level, yeah, it's kind of, yeah, rant over pretty much. Okay, these are just some details I already explained. They have a huge 7 billion pre-trained language model, they freeze it, and that's how they train the model. I also explained this one, how do we map the images into tokens, which a language model can then parse. Okay, I'll just skip all of those small detail. They're using positional encoding that help them, and let me focus on this. So important thing I want you to notice is that they have a bunch of different ways to prompt this model so that it can generate the answers much better. And here's one example. So they have a pretty intricate like terminology here. So 2 ways, 0 repeats, 2 inner shots. So let's see what that means. So first they have this task induction, which they quantitatively showed it helps a lot. So answer with DEX or Blicket kind of prompts, kind of tunes the model into answering with these 2 words in a sense. And then they have, so 2 shots, basically this is the first part. And the reason it's 2 ways because we have 2 made up words like Blicket and DEX here. And because the reason it's 2 inner shots is because they have 2 independent examples here, as you can see. And finally, they prompt the model, and Blicket would be the correct answer because, as you can see, Blicket is lying. Okay, and the last task they'll evaluate is this one, where again you have to associate a visual category with a novel word, and finally you actually not only have to output like here it's basically recognition. You recognize it's a lion and you output Blicket, but here you have to reason because it says what is the question says what is the DEX made of. So you first need to understand that DEX is a table, and then you need to understand what it is made of, and the answer is wood. So this is the final task they evaluate this frozen model on, and now let's see the quantitative results, okay? Here are the results for the visual question answering, and there are these baselines which I'll shortly explain now. Especially this blind baseline. So the strength of the pre-trained language model is a double-edged sword. It powers the generalization abilities of Frozen, but also enables the model to perform surprisingly well without considering the visual input at all. So you can learn to ignore the visual input and still answer the question. So to guard against this possibility, we also trained blind baselines in which the image presented to the visual encoder is blacked out, but the COMNet weights are still trained. This amounts to prefix tuning. So just as a short reminder how it works, basically here, instead of an image for these baselines, what they'll do instead is they'll just black out, or blue out in my case, these images. And so what happens is basically the model will have to learn some representation which is constant, which won't change because it will only be presented with black images. And so that constant kind of needs to help in this captioning task. And so that's why they call it prefix tuning, because it finds some representation that helps the overall system do better job at captioning. Okay, so that's one of the baselines, the blind baseline. And having explained that one, let's now focus on the quantitative results. Okay, here we are. So Frozen. here is the version we were talking about. Here is the version trained from scratch. So that means you just stitch all of the weights in the pre-trained transformer and train it from scratch. Here are the setups they have. So there's 0 shot, 1 shot, 4 shot, etc. And we can see that as we add more examples, we have this trend that the accuracy is improving, which is desirable. Okay, we see that the from scratch model totally fails. We see that the fine-tuned model is worse. So fine-tuning. So basically here they do not freeze the language model, but they initialize the model with a pre-trained weight. The blind baseline, I've just explained it as well. So again, Oscar is some dedicated baseline. You can see it's much better than Frozen, but the whole point here is that we have this improving ability that also was pertinent to GPT-3 models and language models in general. So that's cool. Here you can just see when you additionally fine-tune on this very dataset, visual question answering dataset, the performance obviously ramps up, and that's expected, I guess. Now, the second thing here is they test on this OK VQA dataset. So this dataset contains those examples where you need some additional knowledge base in order to answer the questions. And again, they show that the model improves with additional examples. As a new baseline, they use this 400 million parameter model. And by the way, this one has 7 billion. And again, obviously, the bigger the model, the better the performance. It's something that's not that surprising, I guess, like in 2021. And yeah, again, this baseline is much better. They just want to stress out that we have this improvement like being transferred to this multimodal setup, and that's cool. Okay, so that was the first experiments they did. Here, let me just kind of reiterate this because it's really important. So this conceptual captions dataset is hypernymed, meaning that, for example, proper names are replaced with a general person, a word-like person, okay? So this enables us to rigorously study the transfer of actual knowledge because all knowledge of named entities comes from language model pre-training. Consequently, when we show the model an image of an airplane and ask who invented this, the visual encoder has determined that the image contains an airplane, and the language model has used this to retrieve the factual knowledge that airplanes were invented by the Wright brothers. And finally, jumping to fast concept binding, these are the last tasks they tested this Frozen model on. Let me just kind of connect this table with the actual task. So this is the task at hand. We have this visual binding task. So this is a two-way binding because we have, again, two novel made up words, text and Blicked. They also show like 5-way binding task where obviously we have now 5 made up words, and we'll soon see that it fails on that one, but it succeeds on the 2-way binding task. So on the 2-way binding, you can see again they have a bunch of different ways to prompt the model so that they can elicit better outputs. And again, here you can see it's improving with more examples. Second thing they tried is they used real names instead of those made-up words. They do this so that they can quantify how harder it is for the model to learn the binding and how hard the task itself is. And you can see, so this kind of bugs me. I'm not sure whether this is a typo, but like it has better performance, and then it kind of saturates after 3 examples. Again, this annual baseline is better. As I mentioned, 5-way binding fails. So here it's literally like same as random chance, 20%, and it kind of improves here, then goes back. So yeah, it's inconclusive here. They mentioned here somewhere here, just a sec. So in table 4, we show that the observed effects on open-ended mini ImageNet do not transfer to the 5-way setting, where Frozen is not significantly above chance. This shows that learning to bind 5 new names to 5 visual categories in a single forward pass is beyond the current capabilities of Frozen. Okay, so it kind of fails there, and they leave it up as a future research. The final task is the one I showed you, where you need to, aside from fast binding, you need to reason. Not much new conclusions can be made here. So again, it's improving with more examples. The interesting part maybe is, so if we focus on this blind baseline, we can see that even repeating, so again, remember the image is blacked out, so we just repeat the text a couple of times, and those linguistic cues help boost the performance of this blind model, which means that these improvements above basically are a combination of both linguistic cues as well as the visual cues. Okay, I think that's pretty much it. I like this paper a lot. I like this inclusion of visual information into this whole pipeline. It slowly starts resembling the way we humans operate. So we have these we have vision obviously, and we kind of somehow represent that information, and then we have this computation engine inside our head. By the way, one of the previous papers called pre-trained transformers or universal computation engine or something, they showed that if you take a huge pre-trained language model and you just tweak some layer norm parameters and some embedding weights, you can basically fine-tune it very fast onto novel tasks, and that's cool. I guess this work is a follow-up in a way, and yeah. Having said that, I hope you liked this video. If you did, consider subscribing, sharing, and until next time, bye bye.